Welcome to Dr. Jimmy's Applied Calculus, Section 4.2. We're going to look at derivatives again and some very basic rules for manipulating the derivative. So before we get too far in considering derivative and those rules, a little treatise here on operations and the order that we perform operations, or we might say order of operations. So in many cases we have two operations we're using. So one of those things that you first get introduced to is operations of addition and multiplication of numbers. And so you can do addition, something like x plus y, and then we can do multiplication. So we might take 4 times this addition. So when we do that, we're specifying that we add first and then multiply. So if we interchange the order, we could multiply first. So 4 and x and 4 and y, and then add. So on the surface, two different things: add first or multiply first. And so with those two particular operations, you learn, and it's drilled into you over and over, that they are the same, and a very useful little rule. But then we run into other places where we might have the square operation and addition operation. And so we could add first and then square, or we could square first and then add. So same operations, opposite order again. And although very frustrating, because we spend a lot of time learning the first rule for two particular operations, multiplication and addition, when we get to this basic operation, squaring something and adding something, they're not the same. The square of the sum is actually x squared plus 2xy plus y squared. So we have to get used to the fact we really like this basic rule that if we interchange the order of operation, it's all the same. Oh, but then unfortunately it isn't always the same, depending on the operations involved. So when we write something where the operations have been interchanged, we should take pause. Is it going to fit into this category where it doesn't make any difference? Or does it make a difference? So now let's take that back to derivatives. So the operation of doing a derivative, or given f, computing f prime. So let's intersperse that with some other operations. And so multiplication. So multiplication by a fixed number constant. So we're going to take and use C for that fixed number. So if X changes, if the variables change, this is just a constant. So it would represent maybe a 2 or a 6 or a -7. But it's not going to change on us. So that's very important that this creature is just representing a constant. And so if we do these two operations, we could take and perform the operation of the derivative and get f prime of x and then multiply. Okay, so derivative and then multiply, that's an order. Or if we interchange the order of the operation, we could take and multiply first. So before we consider the derivative, we could multiply, find an expression, and then worry about the derivative. So notationally looks about the same, but there's quite a bit of difference conceptually. Derivative first, then multiply, multiply first, then derivative. So we found out in general we should be careful. These things don't always come out the same. That's what's nice about derivatives. Is that they are. So that's one first very basic rule for derivatives. Then we could look at the derivative operation and addition operation. So we could look at derivatives. So I might have two expressions, compute those derivatives, and then add. Or if I did the operation of addition first, find an expression, a new function, and then differentiate. So, same two operations, but opposite order. And just like before, we should be careful. That doesn't necessarily mean we get the same thing, but for derivatives and addition, very nice, we do get the same thing. So we can do it either way. So those two rules. So we'll come back and revisit these, but the order of operation won't make any difference if we're multiplying by a constant, or in the case of terms of an expression, considering the coefficients. And considering terms of an expression, it doesn't matter if we take the expression as a whole, add first, or take it apart and differentiate first. So, before we continue with those, let's get a rule which gives us some of the pieces of expressions. And so looking at power expressions. So something called a power rule for the derivatives. So we looked at a power rule for definite integrals, or those sums. Here we're going to look at a power rule when we use this definition, the limit, that gives us a derivative. So again, just a basic power, x with an exponent some n. And so if we take that and look at the derivative in this notation, dxn over dx, the derivative, there's a rule that it's the exponent n times a power where the exponent has been reduced by 1. So this works for any exponent n. So now, things like the derivative of x cubed will be 3x squared. The derivative of x minus 2 exponent would be minus 2x, well, subtract 1, minus 3. Derivative of x 1/2 as an exponent will be 1/2 x, subtract 1 from the exponent, minus 1/2. Now there are, as we've seen before, some expressions aren't written directly as a power, but we can write it as a power. So the derivative of 1 over x, to use the rule, we need just x with an exponent, but that's possible because that's equivalent to x with a negative 1 exponent. And then we can apply the rule minus 1x and subtract 1, minus 2. Of course, if we want to put it back into the original fractional form, that's 1 over x squared. Or things like derivative of the square root. Although not written as a power, we can. And so it becomes a derivative of x with an exponent of 1/2. So that's back to 1/2 x, subtract 1 from 1/2, minus 1/2. Or in terms of the original radical form, 1 over 2 square root of x. So we have a power rule that will allow us to deal with any possible exponent. Now we can put this together with the rule that we can either take terms together or separately and differentiate. Whatever we know about the derivative without the coefficient, we know it's just multiplying by that same coefficient. So, using these rules together, we could take an expression like 3x squared plus 5x minus 6 and come up with an expression for the derivative, because it said we could take each term separately and worry about the derivative. So that's it doesn't matter whether we take this whole expression or pieces and differentiate and then add them together. And then the other rule says that, well, it doesn't matter whether we multiply by 3 first or consider the derivative and then multiply by 3. So it means we just need to differentiate for powers. So here 3, and then this derivative is 2x to the first. This one would be 5. This would be 1x to the 0. And then the derivative, well, we could look at it the different ways, but if it's the change, there is no change in a constant. So we would have 6x, this x to the 0 is actually 1, and we get 5. So the derivative expression would be 6x plus 5. Now, here's g of x is equal to 4x minus 10. So we could consider rules. We could do something like I did above for these terms. On the other hand, once I get first degree and constant, this, we know what that slope is, don't we? So in that case, we could say, what's the slope of the line 4x minus 10? That should be the derivative. Or any x term, the derivative is the coefficient, and a constant derivative is 0. Okay. Although the power rule works in each case, it's kind of a long ways around once we already know the derivative of first degree and constants. Now, I gave some rules like a constant times an expression. We could differentiate either after multiplication or before. We might address, well, where does that come from? And so a real quick look at that. So the derivative, if we multiplied first, would look like this, a change in c times f from x to x plus h. But if we factor c out, it's not affected by the h. So we see the definition of the expression f times c. We could also look briefly as I said, if we took f of x plus g of x, any two expressions, differentiate, it should be no different than doing the derivatives first and then adding the terms together. So if we think of the derivative after adding, if we added these together, evaluated x plus h, subtract what it was at x, and then divide by h. That would be that derivative. But then if we rearrange the terms, we can take f of x minus f of x plus h minus f of x. Those two terms all divided by h. And then we can separate out, we have the term gx plus h minus g of x. Those two terms divided by h. And write it as the sum of the two. So algebraically equivalent, and so take that apart as two separate limits. So again, we have the limit for this and the limit for that. So it does work out nicely. And we're going to use those rules. Now, the power rule let's look at that a little bit in terms of a specific power. So let's take something like x cubed and then look at the derivative. So the derivative would be this difference. We would have x plus the change in x cubed minus x cubed all over h. So, as long as the 3 was replaced by a whole number, we would do a similar thing. We would multiply out this expression x plus h. So, one part of that multiplication will always be this x cubed, some other terms, and eventually h cubed at the other end. And so in between are other things. We get x times h times another h, and x times another h. So I'm going to shorten this discussion a little. Allow the reader or the student, if you wish, to verify that you would end up two more terms, which would be 3x squared h and 3x h squared. Now, at this point, if I had changed this number to maybe 16 instead of the third power, it would still start with x to the 16th, have all these other terms, each one with an h, which is important here, because the next step always gets rid of this term that has no h. So, as long as we have a whole number power, this phenomenon that the non-h term adds to the original, and we end up with every term in this sequence has an h. So if we begin dividing h out of each term, we can take the limit. Now, it's important that once we divide out an h, there's only one term that doesn't have an h. So this multiplication 3 times of x plus h generates an x cubed term. It generates an x squared term, and others, x in lower degree. So that would always be the case no matter where we start. X to the 16th would have an x to the 16th term, and x to the 15th term. And so here the limit is just that second term with the square. So the derivative will always be 1 less in the exponent. And then where does this come from? Well, if you multiply it, it's true that you would start this multiplication with a to the n, and the next coefficient is always the same as the power in that multiplication. So you can do that with a few different things. That's what you get with a 2. You can try it with a 5 or a 16, and notice that this is always that same number. So that's a little justification of why this rule works. Subtract 1 from the exponent after you've multiplied by that same exponent.